Okay, well, I'm trying to record this for Cameron and Carly, and certainly we miss you probably a lot more than you miss us. So hope everything's good for you on the East Coast. But anyway, we're looking at inverses of functions, and basically just kind of starting to talk about that last time in section 5.1 or 5-1. And what we talked about is like, hey, if we have f of x equals x cubed, how do you undo that? Well, that's going to be undone with an inverse function. G of x is going to be the cubed root of x. Basically, if you take 10 and cube it, you get 1,000. And if you take the cubed root of 1,000, you get back to 10, right? So the reality is we need a definition, formal definition on what an inverse function is. But before we do that, we're gonna define what one-to-one is, I think. And anyway, well, before let's just do composition of functions here. If I do f composed with g evaluated at x, that's f composed with g of x is f evaluated at g of x. So we put in g of x first. That's f evaluated at the cubed root of x, because that's what g is. So we plug that in right there. And then f of anything is that anything quantity cubed. So this is cubed root of x quantity cubed, which is what? That's equivalent to x. All right, and then what if I do g composed with f evaluated at x? By definition is g evaluated at f of x. Put f of x in there first. F of x is x cubed, so it's g evaluated at x cubed, and g of anything is the cubed root of that anything, so it's the cubed root of x cubed. Of course, this is also equal to x. And we noted that y equals x is the identity function. We mentioned that last time. So in general, this is going to be true. These are going to be inverses of each other if and only if the composition of functions both ways equals the identity function. So these are going to be inverses of each other, and the way we're going to write an inverse notation is f to the minus 1 power. So if f of x equals x cubed, then f inverse of x, we can write like this, is going to be the cubed root of x. And of course, in this case, the domain of f and the domain of f inverse is all real numbers. The other visual, Garrett, get back in. What are you doing?
I don't have internet.
He's got the dinosaur game.
Yeah.
Wow. All right. Well, if you have to, you can look on at a 6-foot distance from Jared's. Anyway. All right. So let me clear this screen off here. Just going to do a quick graphical application here. You know, if I have f of x was x cubed, that's kind of that swerve graph, right? But then what we can do is we can switch the y's and the x's to come up with the inverse. So if we have f of x equals x cubed, but let me just go back to that. We'll just call it y equals x cubed. If I want to come up with the inverse function, I switch the x's with the y's. And if I switch the x's with the y's, then I've got x equals y cubed. And then I want to solve that. I want to solve this for y. And if I solve that for y, then y is going to equal the cubed root of x. And of course, this is going to be the inverse. So this is f inverse of x. But it's like switching it about the y equals x line. And so if I mirror image that through the y equals x line, there's the inverse function right here, cubed root. And so that makes sense. So from a graphical standpoint, once again, we're just doing a 180-degree flip about the y equals x line to come up with the inverse of a function. So we do need to be a little bit careful. So while I'm on the graphical concept here, let's go back and just kind of remember, if I've got, we talked about this before, but if I've got f of x equals x squared, and I'm trying to look at an inverse of this, if I do the same deal where I got the y equals x identity line right there, and I flip this, what's it look like? it's going to look like this here, which is fine, but it's also going to look like this. And of course, that's not a function because the same x would intersect twice. So what we really need to do is we need to restrict the domain here. And so if I get rid of the left side there, then I'm not going to have the bottom. So if I'm only looking from including 0 to infinity, then the inverse is okay on this. So f inverse of x is the square root of x, but on the positive real numbers including 0, or if you prefer, including 0 to infinity. So we're okay there, just starting at 0 and going to the right. Okay, so that's some graphical explanation of inverses. And now we can go back. So the question I did have on the board while I was getting this logged in, I said, hey, what if we have f of x equals x squared minus 4? How do we find the inverse of that? Well, we can do it the same way. So y equals x squared minus 4. Did anybody come up with the inverse? And if I switch the x's with the y's to find the inverse, then I'm going to have x equals y squared minus 4, and then solve it for y. So add 4 to both sides. That equals y squared. So then what's y equal? Y equals plus or minus the square root of x plus 4. Of course, it's not a function if we take both of them. So I'm going to have to restrict the domain here and take the positive one. So the x squared minus 4 here. Sorry, let me draw the xy axis here. There's the xy axis. X squared minus 4, what's that look like? It's a downshift, right, of a parabola of the y equals x squared. But what we have to do here is restrict the domain, not look at the left side or the negative x's there, and flipping this here should end up looking like what? Y equals square root of x plus 4 goes left 4 units, which that's only 2. And we left 4 units starts like right here and goes like that. So it's square root graph with a left shift, half a parabola over there. And of course, we're leaving out this part of it as well, which is minus square root of x plus 4. But anyway, this was a left shift. So remember all that stuff we did back in chapter 1? Base graph shifts. So I'm going to really focus on base graphs and base graph shifts and stuff you can handle, as I mentioned. So there's a lot of stuff in here that says use a graphing calculator and get in a window and all that stuff with old technology, which any computer is going to have that. You can use Desmos on your cell phone as a graphing calculator application. You can do all that type of stuff, but we're going to keep with concept and try and deal with functions that we can handle, that we can come up with. So I'm not, when it says graphing calculator, like I'm not too worried about, I'm not going to get bogged down on that type of stuff. They do great stuff. You can tell what to graph, but we're going to do the analytics on our side. All right, so a couple other definitions. One is a one-to-one. What's a one-to-one function? So f is one-to-one, and I believe they use dashes there. So one-to-one, but mathematicians don't like writing stuff out, so we're going to use 1-1 is kind of how I do one-to-one. What does that mean? Remember the inputs, the x's that you put into a function. What are those? What's that called? The set of x's that you can input. This is class participation time. All x's that you can plug into a function is part of the function's what? Domain, right? And then the outputs that you hit are the range, all right? So what does that mean? So like, what's one-to-one mean there? So this is true if and only if every, I'm just gonna use slang here. Every input has one and only one output. Did your screen just shrink or just mine? Has one and only one output. So that means for every x you put into the function, you're only hitting one height. But for every height, there would be only one x that hits it. So, and vice versa. Okay. So anyway, so let's look at an example of this, and then the question is, how do we come up with it? Formally, what is, I guess the book has the formal definition. I gotta erase it. Oh no, I don't want the eraser. I will erase you. All right. So come back, let me get to the drawing. Anyway, F is one, so here's the book definition. F is 1-to-1 if and only if x1 equals x2, so you have two different x's, would imply that the outputs have to be the same as well. Okay, so that's one way. This is equivalent to the definition on page 425. But anyway, we could also say F is 1-to-1 if and only if x1 is not equal to x2. So if you have two different x values, then that's going to guarantee that the outputs are not going to be the same either. So what does this mean from a graphical standpoint? It means from a graphical standpoint, let's look at y equals x squared, or f of x equals x squared. Is that 1-to-1? Yes or no? No, this is not 1-to-1. And the question is, why? Well, if I have, if I got x equals 2, I'm hitting a height of 4, right? But if I have x equals -2, I'm also hitting a height of 4, right? And so what type of test does this have to pass? So hopefully this is stuff you had.
Horizontal line test.
Yes, so basically F is 1-to-1. If it's gonna, if you know what the picture looks like, which we don't always know what the picture looks like, but it has to pass the horizontal line test. So this hopefully part right here is review. It's got to pass the horizontal line test. Okay, so clearing that off, moving along. So some of this stuff is kind of easy, fairly easy review. But the horizontal line could intersect at most one point. Okay. Then we have a theorem. So a couple proven facts in this chapter, but what's a monotonic function? What's that mean? What's a monotone function that's monotone? A monotonic function. What's that mean? No. Well, mono. Yeah. I used to make fun of people that got mono because I said, what'd you do, lick a doorknob? But see, now when you get COVID, I can say, what'd you do, lick a doorknob? Maybe we should lick more doorknobs and, oh wait, I can't say this on film. Yeah. Anyway, what's monotonic? We had this in Calc 1. Just because you didn't have it on your cheat. Hey, it's nice you showed up, Garrett. Anyway, monotonic function is either increasing or decreasing. One or the other, not both, on an interval. Okay, increasing or decreasing. Now the book, when they say increasing, that really some books would call that strictly increasing or strictly decreasing. Your book just says increasing or decreasing. That means it's going strictly uphill. That means that for the increasing, if x1 is less than x2, then what's that going to guarantee? That the output f of x1 is going to be less than f of x2, strictly less. So in other words, if on the graph, if I've got x1, x2 right here, then this point, left output is going to be lower than that. So I'm going uphill left to right. Okay, remember that? Anyway, I haven't said anything about the theorem yet, so I got to go back. What is our theorem? A monotonic function. It keeps changing the size of my screen. I hate this computer.
Is 1 to 1.
Well, a monotonic function on an interval is 1 to 1. That's good. So that's pretty obvious, right? As far as every input has exactly one and only one output, it's going to pass the horizontal line test. Shay, get back in. What are you doing?
It's your Wi-Fi.
It ain't my Wi-Fi. Don't you blame this? This is like I know what your parents feel like right now. You blame them for stuff that's really your fault. Okay, but so
This was happening at home.
if we're looking at that, that's increasing, right? But what's nice, I hear, as much as you're complaining today, you're going to get out in the real world real quick when you graduate high school, assuming you do. And, huh? Yeah. And then you're going to find out what hard is. All right. But anyway, so every input has exactly one and only one output, right? So that's 1 to 1. If I'm strictly uphill, left to right, then I'm going to be on, on whatever interval I'm looking at, then I'm monotonic. And then that leads to, hey, welcome back, Shay, or should I say Captain America.
Yeah.
All right. So ironically, Shay had to, meet me separately because you had some kind of appointment that I can't disclose due to HIPAA rules. Anyway, he said aye, Captain to me, and then he ends up being Captain America. Like, who knew? Yeah, and so I'm like, how can I be the captain if you the captain, America? Anyway. Okay, so here let's definition of inverse of a function. So let's look at our definition for inverse. First of all, what do we have to have for f? If f, so I'm not going to write f of x every time, but f is a function. I'm not going to say that f is a function. F and g and h, those are always going to be functions for me. If f is a 1-to-1 function, okay, that means we know monotonic functions would fit into this. Then f inverse of x is the inverse, which is what we're defining, inverse of f on that interval, if and only if what? If and only if y equals f of x implies x equals f inverse of y. What does that mean? The domain of f inverse equals the range of f, and the range of f inverse equals the domain of f. Okay, so we kind of have that both ways. So they got to match up. Anyway, and then we define the identity function, and so we have a theorem or a proven fact. So that didn't really say anything that is very exciting, but it's just kind of a, the definition. Anyway, the theorem is this: if f is 1-to-1, so it's a 1-to-1 function, and has and if it's a 1-to-1 function, we know it has an inverse, right? And has f inverse as its inverse function. then f composed with f inverse of x is going to equal x for all x's in the domain of f. And we also have it the other way around. F inverse evaluated at f of x is also going to equal x, the identity, for all x's in the domain of f inverse. Now, how could I rewrite this? Were we writing that? We could write that f composed with f inverse evaluated at x, and I could rewrite this one as f inverse composed with f evaluated at x. But anyway, those both equal the identity function when you go back and forth. Okay? And once again, I've already showed you how to do it. You switch the y's and the x's, and then solve. So clear the annotations. Sorry, I was just talking out loud. Example, okay, what if I have g of x equals 4x minus 5? Find f inverse, or at g inverse. Man, this is horrible. 4x minus 5, go. That's yours. That's for you to do. It's 4x minus 5.
All right.
Something happened. My board got smeary there. 4x minus 5. What's g inverse of x? First of all, is it okay that it exists? What's the domain of g? All reals. What's the range of g? All reals. Anyway, is the inverse going to exist? Can somebody tell me that?
Yes.
No.
Well, this is, if you graph it, what's it look like? With a slope of 4, y-intercept minus 5, but this is increasing on all real numbers, right? So, which means it's monotonic, which guarantees the inverse is going to exist. So the question is, what is the inverse? I already showed you how to do it. Who's got it? This is class participation. X plus 5 all divided by 4?
Yep.
That's the conjecture. X plus 5 all divided by 4. Okay, so we talked about how to do this. So if I call this y equals that, and then switch the x's into y's, and then I've got x equals 4y minus 5, whoops, minus 5, and then solve that for y. So undo order of operations in reverse order. So I add 5 to both sides, so I got x plus 5 equals 4y. Then I'm going to undo the multiply. So when I evaluate the right side, so if you get into something that's awkward, you can say, hey, what do I do here to the y? I multiply by 4. So the first thing I do is I multiply by 4, and then the second thing I do is I subtract 5. So you want to undo those order of operations in reverse order. So how do I do that? So the first thing I'm going to do is I'm going to undo subtraction of 5, which is add 5. Do that to both sides. And then the second thing I'm going to do is undo the multiply by 4, which is divide by 4 on both sides. So anyway, so y equals x plus 5 all divided by 4. You're correct. Okay. And of course, the domain of G inverse and the range of G inverse is also all real numbers, right? So if I put G inverse, domain of G inverse, range of G inverse, all real numbers. I got a question for you. Is that going to be increasing or decreasing?
Well, I do some quick math.
Increase.
That's also increasing. So I did just want to point that out. So really what's going on here is, you know, you have, we could rewrite that as 1/4 x with a swervy board plus 5/4, right? So it has, for the inverse, so 5/4 is up here with a slope of 1/4. But anyway, it looks like that, flipping about the y equals x line here. Right? So anyway, both of those are increasing. So just because you take an inverse of an increasing function, it doesn't flip it and guarantee, you know, it doesn't make it decreasing necessarily. It could, but it doesn't. Like in this case, it doesn't. Okay. So I just wanted to kind of point that out so that you don't start inventing rules that don't exist. And then the biggest thing here is trying to come up with calculus applications of this, because you've already had all this stuff, hopefully, right? So, yeah. Yeah, preferably in a facility. All right. All right, so if we have, here's another couple theorems. This one's on page 432, so we're flying through the material here. So if f is continuous and increasing on the closed interval, so f is continuous, that means we can draw without lifting our pen, right? There's also 3 bullet points, so you're continuous at a point if f at x equals a, if f of a exists, if the limit as x approaches a, if f of x exists, as you approach from both sides and they're equal, right? So basically we can draw the graph without lifting our pen, and then of course you have right-handed continuity at x equals a and left-handed continuity at x equals b. When it's on a closed interval, but we're saying it's continuous and increasing. So it's also monotone, right? Which means that we're guaranteed to have an inverse. So if we have both continuous and increasing on the closed interval a to b, then what do we have? 1, f has an inverse, which we already knew from a previous theorem. And f inverse is going to be defined on f of a to f of b, f of a to f of b, and then 2, f inverse is increasing. So in this case, so if it's continuous and increasing, then the inverse is going to be increasing as well, which is what I just showed. So when I said when you take the inverse, it could make it decreasing. I don't know, then it wouldn't be continuous and increasing, right? So that kind of disputes what I just said. So it wouldn't be a continuous function then. And then the last thing, the inverse is going to be continuous. So I guess you could say what I said, that it could be not if it's continuous. If you have continuity and increasing for your function, then the inverse is going to be continuous and increasing on this interval. Okay, so that's kind of that's a nice result to kind of verify what we saw with that line inverse that we just looked at. And then guess what I can do? I can change that word continuous and increasing to f is continuous and decreasing, and then guess what? You're going to have f inverse is going to exist, and f inverse is also going to be continuous and decreasing. Okay, so let's go back and let's get to the theorem that we need to know that's actually new. So we're going to let f be continuous and monotonic. I'm just going to say mono. So that means it's either increasing or decreasing, one or the other, not both, on the closed interval a to b. Then, what can we say? Excuse me. No, not then. And. Sorry, I got my book on the wrong side because I'm on the right page. So I got to switch. Let's see. Take me back. I don't want to clear that. I just want to erase this. So I'm continuous on the closed interval, a to b, and let y equal f of x, which that's kind of a duh thing, so I wasn't going to put that in, but they did. So first of all, does f inverse exist? Oh, excuse me, if f prime exists. Does f inverse exist for this function? Does the inverse exist? Let's just answer that first. It does, doesn't it? It has to because it's monotonic, right? So we already had that theorem. But anyway, now we're going to say if f prime, not f inverse, if f prime at x exists and not equal to 0, so excuse me, exists, and f prime at x does not equal 0 for all x in the interval, for all x's in that closed interval a to b. So the derivative is not 0 ever. Then what do we have? Then the derivative of the inverse function why did I write out of the inverse function? I could have just wrote f inverse is given by what? So how am I going to write that? F inverse prime at x, right? So did you know that -1, that's notation. I think I said that before, but I can put a little -1 up there for inverse. So f to the -1 power, we can read that as f inverse. Okay. Anyway, f inverse prime of x is going to be 1 over dy dx. Well, what's that? That's f prime at x, right? So here's one way to write it. So f inverse prime at x is 1 over f prime at x. Yeah, picked a bad time to leave. This is when it gets intense. How does the book write that? They're saying if y equals f of x, and then x equals f inverse of y, right? And so they can say dx dy. So if x is the inverse function, I'm going to take the derivative of both sides of this with respect to y, right? Because the inverse function is in terms of y originally, right? So I take the derivative of both sides with respect to y. So the way I can write this side is dx dy, the derivative of x with respect to y. And what's that going to equal? This is going to equal 1 over, what's f prime at x in general? What's f prime at x? If f of x is y equals f of x, what's f prime? How can I rewrite f prime at x? Take the derivative of both sides with respect to what variable? This one. With respect to x, right? Because f is a function of x. So this is 1 over dy dx. Well, this is just like so this is another way to write the same thing that I had already written there. Well, that's kind of a dumb thing, because if you have 2/3, what's that? That's 1 over 3/2, right? This basically is just a reciprocal. But what did we have? F is a continuous and monotone function, so that way we know the derivative exists, or excuse me, it's the inverse exists, and we're saying the derivative exists and doesn't equal 0. Anyway, the derivative of f inverse is 1 over f prime at x. So let's look at a couple examples. So this is really the key for what today's, outtake on stuff that you haven't had before, right? I would assume that nobody's had this, have you? Like, like even those that took Calc 1, like you weren't looking at stuff like this, right? You take an antiderivative of inverses? Oh, that sounds tough. No, not at this point. No, huh? You mean inverse trig functions? Oh, that's just for fun. Yeah, of course we're going to do stuff like that. We're just not going to use a graphing calculator. Like, we're just going to know what an inverse function, inverse tangent looks like on a graph. All right, so let's look at a couple examples. What do you want to start with? I don't care. Let's just do y equals square root of x. So what if I have f of x equals square root of x. What's f inverse of x? By the way, we're just looking on a closed interval. Well, we can pick any value 0 to b, right? But anyway, we can take any closed interval to the right of 0. But what's f inverse of x? Can somebody tell me? Let me start picking names. Garrett, can you see it? Square root of x. What's the inverse?
I have x squared.
X squared is correct. Okay. And of course, this is also on 0 to infinity. Now, what do we know about the square root of x? We know that this is continuous, right? Because I can draw it without lifting my pen on that half open interval. We also know that it's monotonic because it's increasing, right? It's going uphill left, right. The bigger the x, the bigger the square root. So what am I guaranteed about this inverse by previous theorem? Elijah?
Not 1 to 1.
It is 1 to 1. It's also going to be continuous and increasing, right? That we would say, because that was this part was where we kind of caught what I was saying before when I said it could be, not if it's continuous. Okay. So anyway, this is always going to be continuous and increasing, but we have both of them. Long story short, this is increasing. So therefore, because it's increasing, what does that say? What did we learn at the beginning of today? It's 1 to 1, right? It's 1 to 1 as well, because monotonic functions are 1 to 1, which also means the inverse exists, right? So we got a lot of stuff that kind of works together here. But anyway, what is the derivative f inverse prime at x? We want to know what that equals, right? Well, if you know what it is, it should equal what? F inverse of x is x squared. So what's the derivative of that with respect to x? What is it? 2x. It should be 2x. So let's find out. Let's take let's call this. I'm going to use different colors here. So we're going to call this. We're going to call this y equals square root of x, right? And if I want dy dx, what do I get? Dy dx, by the way, that's x to the 1/2 power, is 1/2 x to the minus 1/2 power. How do I rewrite that? That's 1 over 2 root x, correct? That's dy dx. And then, of course, f inverse prime, how do I rewrite that? I could rewrite that as dx dy, right? Couldn't I? And this is going to be, so what is dx dy? It's going to be 1 over dy dx by the theorem, right? Everybody agree? Okay. Well, so this is going to be 1 over this box, right? So 1 over, wait a minute. Something right here. That's 2 root x, not 2x. Well, all right, so I'm screwing this up because what they're doing here, they have what, let me clear this. This is crap. So here's why. Let me go back. Hopefully I can tell you why. But when they're saying that, what do we have? We had y equals the square root of x. So if they switch the x's into y's, what do we get? We get x equals square root of y. Y equals square root of x.
Does it carry? Does it really?
Oh, I know. Because instead of calling it f inverse of x, they call it f inverse of y. F inverse of y is y squared. That's why they're doing it. But what we do and what we were doing is then we put it back in terms of x. So then what we eventually do is say f inverse of anything is that anything squared, right? But this is why I was getting messed up here, because they're using this. So anyway, what is the derivative of this with respect to y? Is 2y, right? So dx dy is the same as f inverse prime, in this case of y, is 2y, right? And then what did we get? We got, that's not what we got. What did we got when I was plugging in 1 over the box? So 1 over 2 root x, right, is 2 root x. But then we're saying that these things are equal, right? Because this is equal to 1 over dy dx, and that was the box. So are these two things equal? Well, what's y equal? Y equals the square root of x. So they are equal. All right. So anyway, a little bit confusing when you do general functions. It's a lot easier when you have a point. And I am out of time here. I'm going to keep going on this. So actually, I'm gonna stop this video so that it's easy for you to pick up. Those of you that were here, it's easy for you to pick up on the next video. And I'm gonna finish the section out, and you have the evens that are due Monday, ideally Monday. I know, all right, so a couple people are gonna have real trouble getting them due on Monday. Just try and have 5-1 as done as you can for Monday, and I'll clean up your questions. Okay? And read 5-2, because we're moving on to that on Monday as well. Ready, break.